Today we have a special topic to discuss in a webinar. The topic is based on current integration project for Search and Rescue Department in South Korea. The project was delivered with the help of a local partner. During the webinar, we will discuss how to prioritize search area by using state-of-the-art propagation tool HTZ communication by ATDI. My name is Yaya. I'm a senior spectrum engineer based in Sydney office. I've been with the company for nearly 10 years. So I will walk you through the webinar today. So first we're going to lay down the mission scenario. What is the scenario we're trying to model? Also, I'm going to describe the architecture. What are the components, the planning tool, the database integration. Also, we're going to touch on the automation. In fact, I'm going to run probably a demonstration, how automation is going to work. And also, we're going to do coverage calculations and analysis. And we're going to touch also on the accuracy of the modeling. The purpose is to use the knowledge of RF coverage to further reduce the search area. So that's the idea here. The idea is we're going to use simulation tools, digital terrain model, Clara, base station parameters, and so on to estimate the coverage more accurately, and also with the end goal is to reduce the search area. So the scenario I have before me is there's a person lost, okay? It's a missing person, and all you know is the last concurrent seen towers or cells. So the carriers, for example, advise what is the cell ID or the cell ID or the cells ID of the last connected base stations. So this information is going to come very handy, of course, to do the analysis and then establish the search area. So here what we're going to do, we're going to deterministically find the optimum search area and fine-tune it even further. We're going to rely on the carrier or the regulator information. So we're going to get from the carrier the list of connected base stations or cells, and from the regulator we're going to get the public telephony system sites, the site locations, the technical parameters, transmission power, for example, antenna gain, and so on. So these parameters, if they don't exist, we could rely on some templates and existing assumptions. So we're going to use the knowledge of both connected and non-connected, and this is very important. So we're not just going to use the connected cells. Also, we're going to leverage the non-connected cells in order to further perfect the search area. So we know these two cells are connected to the missing person, but these 1, 2, 3, 4 are not connected. So we're going to use both connected and disconnected or not connected in order to try to reduce the search area. What is the concept behind this? Area reduction. So first let's go with a simple case where you know there's only one case where there's only one BTS connected to a target. So it could be anywhere in that area here. Okay, so this is a simple case where you only have one BTS. So your search area is limited to the blue circle. So I want you here to pay attention to this convention here. If you see a red antenna here, you see this one red, that means this site is disconnected. And if you see green, that means this site is connected. Now, if you have more sites are connected concurrently, so obviously this is limiting your search area. So you look at the overlap. So these two sites are connected, and then you're not going to do search for the entire blue area. Instead, you just look at the overlap. This is called overlap. So now not just connected site, but also disconnected sites. So disconnected site, they're going to actually help me reduce the area even further. It claims that coverage as the best server. So best server means dominant cell. So in these locations here where I'm pointing, this tower is the dominant. And if the victim is here, he would have connected to this tower, but he did not. Okay, so which means this area is an exclusion area. So we could exclude from the search area, which is the pink, originally this one. We could exclude from it this area here. So this will further reduce the area, the search area. So it's not just connected sites are relevant. Also, the non-connected sites can help you further optimize the search area by excluding the non-connected best server from the overlap. The scenarios can be even more complicated. You might have a number of sites, not just one or two or three. So here you see we have 3 towers connected, 3 towers, and with this overlap pink area here as the search area. Now you see here we have 1, 2, 3, 4 disconnected. So these disconnected sites, the tool will use this information to reduce. You see, we excluded a part of the area and part of the area because these cells are dominant. So we could exclude them and further reduce the search area. So this is the convention of area optimization. So the examples I gave you before were based on circles, okay? So radius or search parameter. So in fact, you could deterministically predict and analyze reception. And we're going to use knowledge of the local area, such as the digital terrain model, the clutter, and the base station parameters, and so on. So we're going to use the antenna, the sectors, the azimuth, orientation, tilting, and all this technical information available to us in order to further optimize the model. So this is an excellent example. So on the left-hand side, you have a traditional way where you go and assume that the coverage is a radius, the coverage of a site. And that's not the reality of things, of course. So in that radius is going to give you, in the radius approach, is going to give you a massive area, of course. That's a traditional approach. Now on the right-hand side, you see there is a base station, a single base station with the terrain behind it. So you've got mountains, you've got hills, you've got canyons, you've got all sort of things. You've got also forest, vegetation, and so on. So you're looking on the right-hand side, you're looking at the coverage of one tower. And you see how the coverage is not distributed equally everywhere. So the signal is not distributed in the same direction, and that's because of the terrain. For example, you can see in the area here, the terrain is acting as a natural barrier, and this is limiting reception in some areas. So if someone told me that a person I'm looking for was connected to this tower, there's no point you search in the area, for example, here. You see, there's no point to search here. So we're going to use the realistic environment, digital terrain, the clutter, the environment, the actual environment, in order to further optimize your predictions. The coverage you're looking at here, this is the signal reception level. So neg 115 dBm up to neg 80 dBm. So here you're looking at reception for one site, up to 15 kilometers. And the top, you can see a top view of the base station coverage, and in the bottom here you see it's a side view for the reception along a profile for the specific point here. So I'm going to examine the signal propagation from that tower to that position here. The gray is the digital terrain model. The base station is on the left. The reception point that I specified is here on the far right. And the green one is the signal level across the journey. So you see how a signal is diffracting right here. There's a significant diffraction at that point here. So when the receiver here go beyond that peak of that mountain, the signal is dropping considerably. Okay, so this is where diffraction model start to calculate signal losses. So if you look at this from search perspective, if you know someone is connected to a tower or was connected to a tower, then you know this area here is all, the red area is useless in terms of search. There are 2 types of propagation models. We have what we call statistical models. There is what we call deterministic models. So deterministic are based on rules of physics, and they actually use digital terrain and clutter information as a feedback to further optimize predictions. So ATDI philosophy for signal propagation, we divide it into three components. I'm talking about VHF communication. So we break it down into three components. We've got the free space model. So if it is a free space condition, we apply, for example, free space model. If it is non-line of sight, so there's no line of sight, and that's where diffraction hits. Okay, so we calculate diffraction loss on obstacle. For example, here on the right-hand side, the first image you see a single knife edge. So obstacle. So if there's obstacle in the path, then the signal will diffract based on the clearance ratio. Okay, this is the clearance ratio. So how much obstacle is obstructing into the Fresnel zone. And this is the diffraction. So this is a single knife edge diffraction, but ATDI used Dago 94, which is using multiple knife edges. Okay, so this is adding accuracy to the predictions. Now, and also there are cases where you have a combination of line of sight, no line of sight, and near line of sight. So near line of sight is when you have partial obstruction, such as that case in the bottom here. So you've got partial obstruction for the Fresnel zone, and then the tool can calculate the losses due to subpath attenuation. So the bottom line here is that these propagation models are based on rules of physics, and they increase the confidence in the prediction because they rely on the environment itself. A more accurate model will produce more accurate predictions. And today, this kind of models or terrain or clutter is widely available to everybody. So this is a summary of how propagation works. So let's start by defining these different graphs. So look at the red. The red graph is the signal without diffraction. Okay, or this is your reference model. This is your reference model, like such as free space. So free space is the maximum you can reach. Of course, it's not realistic, but this is serving here as a reference. The green line, the green curve, is the signal propagation along the journey. Okay, so if the receiver is at that point here in the forest here, then the signal level is this. Okay, then when the receiver goes to that spot here, for example, is outside the forest, signal is climbing up. So this signal is varying with a variation of the environment, the geometrical propagation. This is a clutter. Trees, for example, you've got dense trees, you've got light trees. Here, the gray is the digital terrain model. So this is how propagation works in the software. Now let's talk about analysis. What kind of coverage analysis you can conduct? So here we're looking at a composite coverage. So a composite coverage is composed of multiple sites with no discrimination. You can't tell this area, for example, you can't tell who is covering. You can just tell that there's a coverage here. So the gray color is the terrain, and that means also there's no coverage. The blue here means coverage. It doesn't tell you where the signal is coming from or which cell the target will be connected to. Now this is what we call the best server. So best server is similar. So you see it has the same footprint, but it's using more colors to encode the coverage. So here the dark brown means if a person is in that brown area, very likely it will be connected by this cell. The light brown is here on the opposite side. If someone's connected to that cell, very likely he is in that area. Okay, so this is showing which server or which cell is the dominant in a particular area. And this is extremely useful if you want to know where your target is, because handsets typically hand over to the strongest, to the dominant cell in their area. So we spoke about composite coverage. We spoke about the best server. Now overlap. Overlap is identifying the locations or the areas where reception is possible from 2 or more. In that case, I have 2 cells only activated on the map, just to illustrate this. So you've got 2 cells, and the pink color is here. Now the pink means overlap, so handset can detect signals from both towers. This is a zoom in. So this is telling me that if someone is being served by these 2 cells concurrently, he can switch back and forth. Very likely he is located in this area here, because that's the only area or areas where you could get reception from both cells. This is another function that we recently added in HTZ communication or HTZ warfare. This function is called the combined overlap, which is dedicated for search and rescue. So here you can see on the left hand side, you've got 2 activated cells, okay? And the pink area is the overlap. So your target is somewhere in that pink area, but you can see it's a big area. So by adding the knowledge of the best server or for the non-connected sites, so see the black ones here are non-connected. Now the knowledge of the not connected sites coverage, best server coverage more specifically, is going to help us reduce the search area into this. So you see this coverage, this area here, dominantly by these 2 cells. Now these 2 cells are not connected, which means you could remove that area from your search area, and now the search area is restricted to these 2 small patches here. So we managed to reduce from 32.3 square kilometer into only 12.8 square kilometer. So this function is actually making use of all the rules of physics, the digital terrain, the technical parameters of the base stations, and making use of the overlap analysis and best server analysis, coverage, and so on, in order to give you a final picture of where the target area or the search area should be.